So, very good evening to you all and welcome to this class. We will begin with a recap of what we discussed yesterday. Yesterday, we got an appreciation of the fact that we have the Earth's surface here and that we have satellites orbiting over the Earth, and the satellite is collecting information from the Earth's surface. This data eventually has to come down to the Earth. We have our ground receiving station there, and the satellite is information to the ground receiving station, and this data eventually goes through pre-processing, and after pre-processing can now fly. We also saw that we have this satellite will need an energy source, and for the moment the energy source that we're talking about is the sun. So the sun emits radiation, and we say that we have energy interactions in the atmosphere. We also have interactions. We have energy interactions on the Earth's surface, and so we have energy interactions basically. Then we have energy interactions on the Earth's surface. Then we have our satellites, and then we have our ground receiving station. We have pre-processing here. Then we have the various applications. And you remember prior to this as the remote sensing process. Yeah. So we call this the remote sensing process. We stopped yesterday when we got an appreciation that what is actually happening here is that we're dealing with electromagnetic energy, that whatever is moving from the sun to the earth, from the earth to the satellite, from the satellite to the ground station is really electromagnetic energy. And today we want to look at the electromagnetic spectrum. So I have a clip which I want to play for you, but before we play the clip, there are a couple of things we need to appreciate. Electromagnetic energy is driven by an electric field and a magnetic field. Those of you who did physics will appreciate this. And there are various properties that we need to appreciate, and we shall do an appreciation of this in good time. And electromagnetic energy is everywhere around us. And I'm going to play a clip that I would want to share with you. But before that, I will probably copy the link, the YouTube link, so that you can follow it after, or in case you get. So here is the clip, and I hope you will enjoy it, learn a thing or two.
In this episode, we'll be taking a look at the electromagnetic spectrum. Our goal is to understand what energy is and why it's so important in the study of astronomy. If you look back at the history of astronomy, arguably the most important moment came in the early 1600s when astronomer and mathematician Galileo Galilei first improved upon the telescope and used it to look at the heavens above. Galileo noted all sorts of interesting observations that had never been seen before, including the fact that the planet Venus appeared to go through phases, just like the moon. He also noted that the planet Jupiter had several moons of its own. In addition, Galileo was the first to see that there were actually spots on the surface of the sun that moved as days went by. Telescopes have improved quite a bit throughout history. They've grown larger and more powerful. Modern observatories today have massive telescopes with huge glass lenses that allow us to peer to the depths of the universe. We even have a major telescope that's currently orbiting the Earth, which is able to see the very beginning of the universe. But we'll talk more about that later on. So why is it that these telescopes are just so important to our understanding of the universe? What is it that a telescope does? Well, it's pretty simple actually. Telescopes collect light. When we point a telescope up at the sky, no matter how large or small it may be, what it's doing is collecting light that's flying throughout space. It's amazing how much we can learn about the universe just by studying this light. In fact, that's actually what astronomy is. It ends up being the study of all of the light flying around in the universe. It's amazing what we can gain by studying this light. What exactly is light? then? Well, that also can be answered with a simple response. Light is energy. But again, this leads us to yet another misunderstanding. What exactly is energy? Well, if you look it up in the dictionary, energy is defined as the ability to do work, the ability to have an impact on something. What makes it such a tricky concept, though, is that there's many different kinds of energy that are very unique and very different from each other. Energy includes mechanical energy, thermal energy, electrical energy, nuclear energy, light, and heat, amongst others. And all of it can be actively working in the form of kinetic energy, or it could be stored up for future use in the form of potential energy. It turns out that in the study of astronomy, the most important type of energy, and this is shown in its different types on a diagram known as the electromagnetic spectrum. Let's take a look at a short video from NASA which explains what the electromagnetic spectrum is and how exactly it works.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. EM waves travel through the vacuum of space at the constant speed of light. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter. Nanometer. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared wave. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellite, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So the electromagnetic spectrum includes all the types of energy flying around in the air on Earth and in the universe. What you should have noticed from the video is that there's a variety of kinds of energy on the electromagnetic spectrum. They're all different from each other based on the fact that they have a different wavelength, and that's a key idea. Fortunately for us, on page 14 of the Earth Science Reference Tables, we have a chart summarizing the types of energy found on the electromagnetic spectrum. It's a very simple chart that lists the different types of energy and whether or not they have shorter or longer wavelengths. Let's take a look. What you'll notice is that on the far left of the chart, we have the shorter wavelength energy. And you might remember from the video, this is more energetic, and therefore this is more harmful to living things. The shortest of all wavelength energy is called a gamma ray. Then we have X-rays. Yes, these are the same kind that you would get when you go to the dentist or the doctor to check if you have a broken bone. It's a strong type of short wavelength energy. Then we have ultraviolet energy. And these three are generally considered the short wavelength types of energy. On the right side of the chart, we have longer wavelength energy, including infrared, which we feel as heat, microwave radiation, and radio waves. Microwaves are what allow your cell phones to communicate with each other, while radio waves transport, you guessed it, radio signals. Out of all of this energy flying around, there's a very, very small band of wavelengths which humans can actually detect with their eyes, and that is called the visible light energy, or the visible light portion of the electromagnetic spectrum, seen here in the center. What you'll notice is it's a very small portion of the entire spectrum, and what that means is that of all of the energy flying around on Earth and in space, we can only detect a very small bit of it with our eyes. But what we can detect, we can distinguish as the colors of the rainbow. What you notice on the chart is that visible energy is broken down into the 6 colors of the rainbow, with the shortest wavelength on the left-hand side being the color violet. Next to violet with a longer wavelength is blue, then green, yellow, longer still would be orange, and the longest wavelength color is red. So those are the colors that make up the rainbow, and this is what allows us to detect colors in the universe and on Earth around us. What I'd also like to point out is that next to the color red on the chart is the next type of energy, which appropriately is called infrared. And again, we can't see infrared, though we can detect it as heat. Similarly, on the left side of the visible light spectrum, where the color violet is, next to that would be found ultraviolet. This too we cannot detect, though it is flying around in the Earth, emitted by the sun. Ultraviolet is the type of energy that gives us a sunburn when we go outside in the sun for too long. The sun does emit primarily these 3 types of energy: ultraviolet, visible light, and infrared, the majority of it falling in the visible light spectrum. This is fortunate for us because we don't want too many gamma rays or X-rays floating around, as they can harm living things. So let's imagine we took a telescope and pointed it at the sun and collected light from the sun and sent it through a fancy machine called a spectrometer. What we would end up with is a crazy looking image like this. This is the visible spectrum of the sun. And what you notice is that the visible spectrum reflects all the colors of the visible light, essentially the rainbow. But what I also want to point out are these strange looking black lines. Think of these as the fingerprints of the different elements making up the sun. For example, the sun is largely made of the element hydrogen, and so within these black lines is the fingerprint of the element hydrogen. Why is this important? Well, it allows us to determine the elements that make up a star or a galaxy by just looking at the light given off from that star or galaxy. It's amazing what we can learn by looking at energy. We can learn how hot and therefore how large an object is. We can learn what elements it's made of. More importantly though, we can use these spectra to determine if an object is moving.
That is our first video for the day. and hopefully it has given us a good overview of the electromagnetic spectrum. I would like to recap one or two things. So our spectrum, as you saw, so whereas there in the video they started with gamma rays, so we actually begin with cosmic rays, gamma rays, we have X-rays, ultraviolet, we have blue, red. Obviously, we had orange, yellow, or blue. And then we have near infrared. And as you saw in the video, the portion from here to here is referred to as the visible portion. As you can see, it is a very of your whole electromagnetic spectrum. For those of you who did physics at A level, you will recall that we have two ways by which we define electromagnetic radiation. We have what we call, I'll put it here, the wave theory. And the idea behind the wave theory is that we say that, and you also saw it when they were in the video, we saw that frequency of a wave, you saw the definition of frequency, we saw that is inversely proportional to wavelength. So in other words, as wavelength increases, frequency reduces, and we make this an equation by over this, where c is the speed of light. We have a quantum theory of electromagnetic energy, and we know that we say that the energy of electromagnetic energy is directly proportional to the frequency. And if you remember, this is H is Planck's constant. I hope you remember that. So we can combine these two theories, and you will see that to do that, F is equal to C over wavelength, which is equal to Q over H. So we can say that Q is equal to CH over wavelength. And since this is a constant, we can say that the energy of electromagnetic energy is inversely proportional to the wavelength. Now you will realize that in this direction, our wavelength increases, and in this direction, wavelength means that the energy of electromagnetic energy here, if that increases, here it decreases, and the energy in this direction is increasing because of this relationship that we have here. And that is why electromagnetic energy that is tending towards the smaller wavelength is usually high energy radiation, and tending towards where the energy is increasing, it even gets more and more dangerous. So that is why you had in the video, when we have low smaller wavelength in the UV, we can actually get sunburn from it. And then X-ray, we're even now getting to smaller radiation, which has more energy, which is even more dangerous. And if you've ever gone for an operation, if you've ever gone for an X-ray in a hospital, you will realize that they try to expose only the part which needs to be X-rayed. So if you want to X-ray your hand at a place where there was a breakage, they will cover the rest of your body and only expose the area that needs to be exposed. And that is because of the nature of that radiation. By the time we're now looking at gamma and cosmic, we're even now dealing with radioactive. Going the opposite direction, we have already talked about the visible portion of the electromagnetic spectrum. Then we go to the near infrared. Thermo-infrared is as a result of emitting thermal heat. And then our microwave, we have our microwave, and we have our TV and radio. So when you are changing your when you're changing your TV stations, you are moving around here, and also when you are changing your radio station, you are operating within this portion. Now remember, you notice here we're talking about wavelength, but when it comes to the radio, we now are talking about frequencies. Yeah, and from here we can see the relationship between frequency and wavelength. So when as you tune your stations, you are really operating here. When you're changing your TP station, you're operating within there. So we have our microwaves. Now we will come back to the electromagnetic spectrum. Is one of those that is very, very important in our understanding of remote sensing, and I will. Yeah, so we'll come back to this later on. Going back, we have said that we have our sun emitting electromagnetic energy, and you saw that from the clip, a lot of this energy is interfacing with the atmosphere, and we shall have a very good video about that describes the atmosphere. And today we want to look at energy interactions in the atmosphere. Now we have a couple of interactions, and we shall be going through them. We have what we call absorption, we have scattering, and we have transmission. So when it comes to absorption, we have various gases which absorb radiation. We have nitrogen gas, we have oxygen, we have ozone, and these gases, as you will see in a later video, and we also have, these gases absorb various portions of the electromagnetic spectrum. And if you've done your environmental studies very well, you know that ozone, O3, absorbs ultraviolet radiation, and which is why there is a lot of concern about the depletion of the ozone layer. So the fear is that as we deplete the ozone layer, we shall be exposing ourselves to ultraviolet radiation. So we have this happening in, so that's one of the interactions that happens as electromagnetic energy is transiting from the sun to the Earth's surface. When it comes to scattering, when it comes to scattering, we have three types of scattering. We have Rayleigh, I've got the spelling well, scattering. We have my scattering, and then we have scattering. Rayleigh scattering happens up in the upper atmosphere. And then we have my scattering, which happens in the lower atmosphere. And Rayleigh scattering is one which is responsible for the blue sky. And I've got a very good video coming up to describe that. And after that, we have my scattering, and then we have non-selective scattering. A good example of this is your cloud scatter all the radiation. The idea behind Rayleigh scattering is that the wavelength of the electromagnetic spectrum smaller than your molecules and whatever is the upper atmosphere, and because your blue wavelengths are very small, they are scattered, they're dispersed. And when it comes to my scattering, we are talking about the bigger wavelengths interacting with bigger molecules, and yeah, we shall see this clearly happening. And then we have non-selective scattering. And with that, I would like to introduce us to a very interesting presentation. And it's about the first one will be about Rayleigh scattering, and then the second one will be about my scattering. Second one is a bit technical, but you don't need to be worried about that. We will focus on numeric aspects about scattering. So we bring up the video, and so it's a very interesting discussion. Some of you may know this gentleman, and I hope you enjoy it.
Meeting you.
So here's a question that resonates with my
Judd, what's been eating you?
So here's a question that resonates with my, I shall say, razor sharp acumen. Why is the sky blue?
You mean that hasn't been answered since childhood?
You know what? Here's the problem. I asked once, and they were like, "Mind your business," and that was the end of it. No.
Well, you might say, I want to become an atmospheric scientist. It is my business.
That would have
Well,
been
there you go.
That would have been a very snappy comeback for a 3-year-old. Why is the sky blue? Mind your business. It is my business. I would like to be an atmospheric scientist. So.
All right. So the answer is easy to understand. It's just not simple.
First of all, is the sky blue?
Yes.
Okay. Well, at least we got that out.
Does it look blue to you?
It does.
Fine. That's what we're about to talk about.
All right.
So here's the deal. The explanation is actually simple. It just takes a little while to explain.
Okay.
That's all.
All right.
All right.
I have time.
You have time.
I have some time.
Thank you. Thank you.
Yes, and boom.
All right. So we have an atmosphere. We all know this.
Yes, we do.
It's composed primarily of nitrogen.
Okay.
It's 78% nitrogen. It's 21% oxygen, and a few percent other, carbon dioxide, this sort of thing. Mixed in there are particles of like pollen and dust and sand from sandstorms and pollution and smog. And so
Particulates.
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 Okay. Now, light comes from the sun. White light. People say the sun is yellow. It's white.
Right.
Okay.
Exactly.
You've seen the sun in the middle of the day. It's white.
It is white.
Okay. That's the proper color of the sun in the middle of the day.
Let's not get racist.
Let's.
It don't have to be the proper color.
Look, it's just a color.
It's just the color.
Damn, Chuck, why is everything a race thing to you?
Because I live in America.
All right. So you may remember that white light is composed of colors.
Right.
Okay.
Put it through a prism.
That's how you get a rainbow.
Right.
Or you're educated. You said prism, but through a raindrop, it spreads them out into colors.
Right.
And you get the colors of the rainbow. Roy G. Biv.
Okay.
Give them to me.
Right. Red, green, blue, yellow.
Roy G. Biv. Go.
Roy. Red, orange, green.
Roy. Yeah.
Oh, red, orange, yellow, green, blue, and then ultraviolet, but violet.
Biv.
Okay, indigo, violet.
Thank you. Red, orange, yellow, green, blue, indigo,
violet.
Okay, the 7 colors of the spectrum. Okay,
Right.
if you, the way our brain works and the sensors in your retina, okay, the rods, the
Rods and
cones,
cones.
yeah, the rods give you shades of light and intensity. The cones disentangle color.
Okay.
Okay, and you have an RGB cones.
Nice.
Okay, so we get RGB from.
Right.
You've heard that in computers and
right.
the computer screens and everything. Okay, so you're chemically, with the chemicals in your retina, splitting that red light into combinations of red, green, and blue.
Okay.
Okay, broad combinations of these 3. If you have more red than the others, what you look at is going to look more red to you.
Right.
If you have more blue than the others, it's going to look blue. Now here's what happens. White light comes down from the sun.
Is that what it does?
The particles in the atmosphere, some of them are about the same size as the wavelength of blue light. All right. Now, if you have a particle and light, and there's a particle the same size as that light, it'll reflect.
That's right.
Or scatter. That's the proper word. Okay. Bounce, scatter, and so that light doesn't make it straight through. It sends in every other direction.
Oh.
So the light from the sun selectively has the blue removed on its way down to Earth, and the blue scatters into the air, and you have a blue sky.
Very romantic.
It is beautiful. Now it's called Rayleigh scattering. A guy named Rayleigh.
Rayleigh scattering.
Rayleigh. Okay, Lord Rayleigh.
Of
okay?
course, Lord Rayleigh. Indeed.
You figured this stuff out. You a lord.
Right.
All right. So here's the thing. As the sun gets lower in the atmosphere, the path length of the light is much longer through the air. Okay. So in other words, here's your atmosphere. If you're directly above, you're going through like this thickness. As you come down, the thickness gets more.
Right.
Okay.
Right.
Well, more atmosphere, more scattering.
Right.
The sky gets more blue. Okay. So in the daytime, it's quote sky blue. That's actually a pale blue.
Right. It's a very pale blue.
As you go to twilight, that sucker gets deep.
Yeah.
It gets deep blue. And so much more blue gets taken out of the sun.
I just love how violent deep blue is.
It's deep. And if you take out that much blue, the sun ain't got no blue light left at all. So what color is it going to turn?
Kind of red.
Kind of red.
Kind of red.
Kind of red, amber.
Yeah.
Okay? That's why sunsets are red.
Oh, that's...
Because so much blue was taken out.
Right.
That's all it has left to give you is the side of the spectrum where you have red, orange, yellow. Now, sometimes you have a very bright sunset that's not quite deep red. There aren't many particles there for that sunset. There aren't many particles.
Sweet. So that's a kind of a lighter cut, like you know.
Yeah. So the sky wouldn't get as intensely blue when that happens.
Right.
It'll be similar to the sky blue you had earlier in the day. So that's why we have a blue sky.
Nice.
Now, it's also why you can't see stars in the daytime other than the sun.
Well, wouldn't
It's not, oh, you can't see stars in the daytime because the sun is out.
All
That's
right.
not why.
Because the sun is brighter than the starlight that you would otherwise see.
No, that's not why.
Well, see, that's intuitive.
No.
That's how you would think.
It's intuitive, but it's wrong, okay? The reason why you can't see stars in the daytime is because the scattered blue light has rendered our atmosphere aglow. The atmosphere is glowing blue light, and that prevents you from seeing the stars behind it. If you took away the atmosphere,
You'd be able to look up and see the sun.
the sun will be there, but then you like dark adjust over here, and there's full sky, full stars right over here.
Wow.
Over there, all around.
Oh, man. You know what?
What?
If we didn't need atmosphere, I'd want to get rid of it. That kind of sucks.
Okay, so now this is what led to the operational definition of the edge of the atmosphere.
Okay.
Okay? It's kind of operational. It is how high up in the air do you have to go before there aren't so many air molecules above you for the blue light to scatter and prevent you from seeing the night sky?
So it's really about the number of particles.
Yes.
It's not
The density of
about
particles.
the actual.
No, it's just the density of particles, wherever that happens. So we agree, just by convention, if you go up 100 kilometers,
Okay.
converted, it gets 62 miles. 100 kilometers, that's about where the atmosphere is thinned out so that it's no longer scattering blue light. It is no longer aglow. And in broad daylight, you can see stars in the nighttime sky. So that's the operational definition of space.
The operational definition of space is 62 miles above our ground.
Earth's surface, correct.
Earth's surface, where you can just see space, basically.
Because the atmosphere
the
that
atmosphere
remains, there's still atmosphere there, but it's not dense enough to scatter blue light and render it aglow to prevent you from seeing the night sky. Now, I'm not comfortable with that. I understand it.
Okay.
I'm not comfortable.
Now, what's your problem with that?
Because if the atmosphere were half as thick as it is,
Well, then it would only be 30.
it would be
31 miles.
31 miles. That would be space. Well, suppose we're a tenth of it. Then it would be 3 miles. Suppose we didn't have an atmosphere. You'd be in space just standing here, sitting here like this. Should that be called space? That's what I'm saying. It's our definition of space is linked to to the circumstances of our atmosphere.
That kind of makes sense. Well, no, I see what you're saying now, because I was about to say it kind of makes sense because you can't breathe in space, but you also cannot breathe at 35,000 feet.
Right. That's why airplanes have windows that don't roll down.
Right. Wouldn't that be great? Excuse me! Trying to get to Australia.
You tell me which way.
Hey, yeah, you want to go over here and take a look at that cloud?
And take a look before the cloud disappears.
Right,
I'm telling you where to
exactly.
turn.
Yeah, so it makes sense.
It's not about where you can breathe.
Yeah, I see where your problem
It's hard
is.
enough to breathe just on a mountaintop.
Exactly.
You ever run a quarter mile on a mountaintop?
I've never run a quarter mile, period. Are you kidding me?
So now, you might
So
say,
what would your operational definition of space be if it is not indeed this particular
Either in-
atmospheric link?
thank you. If you take out the atmosphere, either you're in orbit or you're going somewhere. Then you're in space.
Oh, so you're using, oh God, you are such a damn astrophysicist.
You got a problem with that?
You are using gravity as the measure of what makes space. At least you are consistent. Oh my
You got a
God,
problem with that?
That is amazing.
And that would be true no matter what atmosphere we had.
I should have known.
What? I'm just saying.
It's like,
Of course.
He's like, no, man, where does gravity fit into this?
Okay.
All right, you talking about
All right.
atmosphere.
So you know how much atmosphere that is? It's 62 miles. That's high up. I
Right.
will show you.
All right. Oh my God, you had to break a globe to show us
I
this.
just took it out. This is like
Oh,
God.
that's just a holder.
This is God holding up the globe.
That's
okay?
Atlas. Okay,
That's
there we
right.
go.
Right. Okay. So I'm going to show you. Here's the United States,
Right.
and I just did some distances I know. New York to Boston.
There we are.
That's 200 miles.
I don't
Okay.
know. Go ahead.
220 miles. No, 180 miles.
All
okay.
right, all right.
So you take a third of that distance.
Okay.
That's 60.
Okay.
Make that go vertically up.
All right.
That's the edge of our 3/8 of an inch up.
3/8 of 1 inch off this is what makes it.
Is
Oh my God, we're in danger. That is not cool.
Earth's atmosphere is to Earth as the skin of an apple is to an apple.
That's what I'm saying.
We don't have much air.
We are in danger.
That air is frail and fragile.
Oh my God.
And you're doing what to it?
And we're doing all kinds of nasty stuff to it. That is unbelievable. Would you eat an apple that somebody just rubbed crap all over? No. Oh, that's insane.
Oh, so sorry, I misspoke. 3/8 of an inch up, that's the altitude of the International Space Station orbiting.
Oh my God, so our atmosphere is actually
Less than
below
that. Yeah, so I'm just looking in here. Here's New York and there's Boston. So you're talking a couple of millimeters, about a millimeter above 2
that's
millimeters.
terrible.
That's the thickness of the air above which we say you entered space.
Why are we not teaching this in school? I mean, seriously. If you ever want to have a true appreciation of just what a delicate balance we live in, that is it right there.
Correct.
Ugh.
Correct.
It's chilling. That's
The
really
skin
chilling.
of an apple is to an apple as the shellac on this globe is to the globe itself.
Ugh.
That is our atmosphere.
Oh my God.
Dude.
Well, there you have it. We're all gonna die.
So that's why the sky is blue.
That's right.
That's why we should look after this little bit of air that we got here on the surface of the Earth.
I'm with you.
And it's why Neil thinks space should be defined by gravity, not by what the circumstances of our atmosphere happen to be.
There you go. You know, I'm gonna agree with all three, man. Yeah, and not because you're my boss.
That's a Star Talk info bit, as always.
Yeah, so before we lost power and I've lost my, so when we were discussing the energy interactions on the Earth's surface, we said there's absorption and it can be, we can have absorption by these gases in the atmosphere. We have looked at scattering, and the idea behind scattering is that we have 3 types of scattering. I think I have, we have Rayleigh scattering, which occurs in the upper atmosphere. And as you saw from that very interesting clip, it's what accounts for the blue sky and the red sunset. We also have my scattering, and I've got a video to demonstrate that. And then we also have non-selective scattering, which is due to the cloud. So allow me share the next video, and let me first, so this is the link for the next scattering that we're going to learn about, which is me or my scattering, depending on what you are used to. And then after this, we shall have one more clip.
Welcome to Electron. In our quest to understand photons better, we're going to talk about what we call me scattering. Now, in a previous video, we already looked at Rayleigh scattering, but now we're going to look at what we call me scattering. So what's the difference? Well, there's 3 different regions of the ratio of particle size to photon size where we have different kinds of scattering. So the first type of scattering is what we call Rayleigh scattering, and I have it right here. So Rayleigh scattering, and that occurs when the particle is less than 1/10 the size of the photon, or at least the wavelength of the photon, because size of photon is still something we need to tackle. It is a difficult concept, and it's really not we really don't think about the size of photon in the traditional way where we can actually put a limit to how big a photon is. But we're getting there. We're trying to understand what a photon is, and so we're going to look at it in terms of how photons are scattered in the atmosphere when they encounter particles in the atmosphere. So when the particles are really small, less than 1/10 of the wavelength of a photon, namely the air molecules in the atmosphere, then we experience what we call Rayleigh scattering. And it turns out that the amount of backscatter, or the amount of extinction, and so when we talk about how much of the light gets scattered away or gets extinct or extinguished or absorbed in any way possible, so meaning how much of the light that is incident on the particles gets scattered back and gets extinguished, and how much of the light continues on forward, well, we call that the extinction coefficient. And that is typically a function of the ratio of the radius of the particle to the size of the photon. And so when it comes to Rayleigh scattering, when the particle is, let's say, less than 50 nanometers, because the wavelength of visible light is somewhere between 400 and 700 nanometers, so we take 1/10 of that, or less than 1/10 of that, we're talking about very small particles like air molecules. And so when the light is incident on that, in other words, photons of visible light, then a significant amount is scattered. And the amount of the scattering, the coefficient, or what I call the extinction coefficient, how much the light is scattered, is simply proportional to the radius of the particle divided by, ooh, that should be frequency, that should be wavelength. There we go. So if the particles get bigger, the amount of light that gets scattered is bigger as well. So definitely a function of the size of the particle relative to the wavelength. But then as the particle gets bigger, and the particle now reaches a size somewhere between 1/10 to a full wavelength in size, so let's say the diameter of the particle is roughly the size of a wavelength, then we go into what we call me-scattering. So what is different about me-scattering? Well, what it turns out is that the amount of scattering from the particle depends upon the direction. So let's say that the photons are incident in this direction, so that's the direction of the photons, and the photons are incident on the particle, which is now bigger than these very tiny particles where we have Rayleigh scattering, then more of the intensity of the scattering goes forward in a single dimension. For example, if the wavelengths, if the photons come in this direction, then most of the scattering will be in the forward direction and very little scattering will be in the backward direction. Not only that, the amount of the reflection or the scattering in the backward direction depends upon the ratio of the radius of the particle divided by the frequency, but not just in a linear relationship, in a kind of trigonometric relationship like a cosine or sine function. It actually varies with that ratio, and then we can see that that variation kind of diminishes as the ratio of r over a gets bigger. Therefore, we have an e to the minus k r over f term. I'll put that in quotation marks because that's something that I kind of came up with to kind of give a feel for that. So the amount of scattering will depend upon some sinusoidal function that seems to diminish as the r over f gets bigger. And so we kind of have these type of components related to the amount of scattering experienced in me-scattering. But you can see that there's some scattering in the up, backwards, and down direction, and the predominant scattering in me-scattering is in the forward direction. As the particle gets bigger, you can see here the particle is bigger again. As the particle gets to be about the size of a wavelength or bigger than the wavelength, then more of the direction of the scattering is forward in the same direction as the approaching photon. And you can see that very little of the scattering goes backwards. At some point, the coefficient of the extinction coefficient becomes a constant. So it's regardless of the size of the particle relative to the wavelength, the scattering then becomes uniform in the direction proportional to the intensity of the light. And so therefore we then have what we call more of what we call optical scattering rather than me-scattering. So the me-scattering then becomes the type of what we call optical scattering. The light simply scatters off a large particle. So me-scattering is kind of the scattering that we find in the in-between stage between Rayleigh scattering and optical scattering. We have what we call me-scattering, and the scattering is kind of a very interesting way in which it's done. So you can see then that the amount of light that gets scattered forward and backwards depend upon the ratio of the size of the particle to the frequency, and you can see that this is roughly from 1/10 the ratio of r over f. Oh, I keep saying f, but I want to say lambda. So we go from about 1/10 the ratio of the radius of the particle to the wavelength of the particle to about 1 times the ratio of the radius to the wavelength. So in this region, when the particle is roughly 1/10 the size of the wavelength to about the same size of the wavelength, in that region the scattering will vary kind of like sinusoidally. And the difference here, in the beginning especially, is basically a 10-to-1 ratio. So it's quite a dramatic change in the scattering as that ratio changes from 1/10 of r over lambda to 1 times r over lambda. And then, of course, it also diminishes like this. And so that's why I kind of threw this in there. So we have a declining exponential function. So as r over f gets bigger, then the variation in the scattering gets smaller. So that's kind of an interesting relationship. So that's what we mean by me-scattering. Notice it's in all directions, but the forward direction, in the same direction as the approaching photons, is where the predominant light will continue to scatter, and a little bit will then get backscatter. Of course, the amount of backscatter does depend upon that ratio. Now, where do we see that in nature? Well, when you look at the sun, especially in the sun when it's kind of a hazy day, where there's a lot of moisture in the air, or a lot of small dust particles in the air, then you look in the sun direction and you can see around it kind of a halo of white light. That halo of white light is really a result of the me-scattering that then hits those particles of that particular size. If the air is very clean, then you don't see that me-scattering. Then, of course, we just see typically just the Rayleigh scattering if the air is pretty well free of the moisture, kind of like the fog particles or kind of like dust particles in the air. Another thing is, for example, when you turn on the beam of your car, the headlights of your car in a foggy condition, then again you see what we call the me-scattering, where we have this back scattering, and that's why you don't recommend to put on your high beams in foggy days, because you get much of that light reflected back in your eyes and they can't see anything. So hopefully that gives you a good idea of what me-scattering is, and again, it relates the properties of photons to what happens in the atmosphere when it encounters different sized particles and the different kind of scattering that the light then experiences. Also, of course, when we have this kind of a...
Yeah, so I think we have seen the most important parts of that presentation, and going back to our whiteboard, basically what has come out of that video is that when it comes to Rayleigh scattering, we are dealing with scattering that occurs in the upper atmosphere. As you can imagine, as the radiation transits through the atmosphere, it encounters increasingly bigger particles, molecules, photons, substances, as it comes closer to the lower atmosphere. So in the higher portion of the atmosphere, we experience Rayleigh scattering, and it mostly scatters the very small wavelength. And when you look at the electromagnetic spectrum, you saw from the electromagnetic spectrum that the blue is has a smaller wavelength, and so it's more prone to scattering. And after all that has been extracted, what we are left with is the red radiation. So Rayleigh scattering is the one which is responsible for those different colors. When it comes to my scattering, that is usually what we refer to as haze, and these are some of the important things that we need to appreciate. Another form of scattering is what we refer to as non-selective scattering. We have looked at absorption, we have looked at scattering, and the next thing that we want to discuss is what we refer to as transmittance. But before we do that, I want us to go back to our remote sensing process. We have the sun, we have electromagnetic energy interacting with the atmosphere, we have energy interactions on the Earth's surface. Energy is captured by the satellite, and ultimately we apply that data. So for us to be able to apply our data, we need to be cognizant of the energy interactions in the atmosphere. For example, if we have non-selective scattering, if we have clouds, we cannot use that. We have talked of haze as an example of me-scattering or my scattering, and there are applications for which we need to correct for that, and we call that atmospheric corrections. We shall be seeing those later on. So let us have an appreciation of interaction in the atmosphere. We have seen absorption, we have seen scattering. We've discussed the three scatterings in the atmosphere: Rayleigh scattering, my scattering, and now we want to talk about transmittance. Now, transmittance is what penetrates through. That is the energy which is not absorbed, which is not scattered, and eventually comes to the Earth's surface. And I have got a very good video which should help us appreciate this more. And it should be the last video for this is the link of the last video that we're going to play, and it's actually a lecture that somebody is giving. Hopefully it will tie together everything that we have chatted.
So now that we've talked about this concept of energies coming from the sun, an assortment of energies, and an assortment of things in the Earth's atmosphere that can either absorb energy, scatter energy, or transmit energy, we can talk about this concept of atmospheric windows. So we say that that the window is wide open to a particular energy if that particular energy can pass through that particular component. We say that the window is closed if either something in the Earth's atmosphere either scatters or absorbs that particular energy, and you'll see what I mean. So we talk about windows in the Earth's atmosphere either being open or closed, and what's happening is that components in the Earth's atmosphere are interacting with particular wavelengths of energy coming from the sun. And it's pretty cool how we basically have a nice little balance of stuff in our atmosphere that protects us and yet allows us to gather energy from the sun. I don't know, I'll show you what I mean. So what this is the radiation curve of it's part of the radiation curve of what energies the sun is sending in all directions. And so remember how you read a radiation curve is on the bottom. We have an assortment of radiations. This is the, over here on the right, excuse me, over here on the left is the shortest wavelength. Shortest. Okay, and down here it starts with ultraviolet, so over here we would have X-rays and gamma rays. And then over here we have the longest wavelength. Longest lambda. We use that symbol lambda for wavelength. And just kind of not necessarily drawn to scale, know that the Earth is oozing its own amount of radiation into space. Actually, it's oftentimes, the way I think of it, is kind of re-emitting radiation that it absorbed from the sun. But this is its cute little curve, and notice that it's over here, and we kind of talked about that before, that its whole curve is shifted here to the longer wavelength, which makes sense. One of the laws of radiation is that if it's cooler, which the Earth is from the sun, then it will kind of peak at longer wavelengths, and it's squattier. But we're going to kind of look at an assortment of gases, stuff that's in the Earth's atmosphere. Of course, the major gas component in the Earth's atmosphere is nitrogen. And the way you read this is the little scale for nitrogen, and this is 100% absorbance. Okay, and so notice that nitrogen does absorb at a handful of wavelengths. Okay, it really absorbs here and kind of moderately absorbs down there. Otherwise, nitrogen is wide open to transmitting, receiving, and allowing these other forms of radiation to kind of come and go. Another important ingredient in the Earth's atmosphere is ozone, and we talked about good ozone and bad ozone, but also molecular oxygen, or O2. About 20% of the gas that you're breathing in is O2. And here is the absorbance or the absorptivity of ozone and O2. So notice that here, okay, we talked about how ozone, O3, blocks incoming ultraviolet radiation, and so the window is closed. We say O3 is closed to incoming of that particular wavelength, ultraviolet radiation. Let's see. We also have kind of a little bit of a spike over here where it blocks incoming radiation at that particular wavelength. Isn't that interesting how it's kind of picky which wavelength it blocks? Now, not only would it be blocking it coming in, but it would also be blocking it going out. See, what else do we have in the atmosphere? We also have carbon dioxide and water vapor. Remember that those two gases are what we call variable gases, aren't they? And it's kind of interesting. These are the, the little mini scale, 0% absorbance to 100% absorbance, 0% absorbance to 100% absorbance of water vapor and carbon dioxide, respectively. So wherever you see the blue, that would be a closed window. So I just think that is so cool. One of the things that I guess I would say collectively with these four kind of little mini showing us where the windows are, notice that nitrogen, carbon dioxide, and H2O, they are all totally open to visible light. Okay, O2 and ozone are have a tiny little bit of a kind of an interaction there with that particular wavelength. That's pretty cool. I wanted to introduce you to, because we'll be talking more about it later, but down here, do you see this where it's short wave radiation? I think it's sometimes called SW for short wave, or long wave radiation, LW for long wave. And I want you to kind of start to be thinking about that. Another word, one way to think about shortwave radiation is, can you see where, if we were going to kind of say the sun or the earth, can you see that the sun is emitting basically shortwave radiation because it's hotter, significantly hotter, and the earth is oozing long-wave radiation. Long-wave radiation would be infrared and infrared, microwave, radio waves. Another thing is, I guess I would just point out this note down here. There is an atmospheric window about here for water vapor and carbon dioxide, and of course nitrogen doesn't interact with infrared radiation. But this window, it said, is important for basically the Earth to kind of vent and cool off. Okay, because remember, those windows are two-way, incoming from the sun and outgoing from the Earth. This window, it said, is important for basically the Earth to kind of vent and cool off. Okay, because remember, interact with infrared radiation. But water vapor and carbon dioxide, atmospheric window about here for water vapor and carbon dioxide, and of course nitrogen doesn't interact with infrared radiation. But this window, it said, is important for basically the Earth to kind of vent and cool off. Okay, because remember, those windows are two-way, incoming from the sun and outgoing from the Earth.
So we have been looking at these key aspects, that interactions that are happening in the atmosphere. We have absorption, we have scattering, we have transmittance, and this is our, what we call our energy interactions in the atmosphere. We have seen that we have these three activities which happen in the atmosphere, interactions in the atmosphere. We can have absorption, and we know that these are the gases that are responsible for absorption. And we saw that ozone is a famous example of absorption of ultraviolet radiation. We looked at scattering. We saw that there are three types of scattering. In the upper atmosphere, we have Rayleigh scattering. In the lower atmosphere, we have Mie scattering. And then as we come further down, we have non-selective scattering. Now, when it comes to transmittance, we saw that transmittance, and as you saw, you have your different wavelengths, and we saw that different gases have different windows, but when you look at the combination, you'll find it is something like that. So that is why when they are designing sensors, they will design the sensors to operate within the atmospheric windows. So your different, yeah. So that is it for today. As you have seen, we have essentially been discussing what happens here, energy interactions with the atmosphere. And tomorrow we shall be looking at energy interactions on the Earth's surface. So do we have any questions? Okay. If there are no questions, I hope that you have got an appreciation of that. So we have, in today's lecture, we have looked at the energy interactions on the Earth's atmosphere, in the atmosphere, and tomorrow we shall be looking at energy interactions on the Earth's surface. So thank you very much. Have a great evening, and let us touch base tomorrow.